Have you ever found yourself just, well, swimming in information, trying to get your head around a really complex topic, and you just feel like you're drowning in buzzwords? If that sounds familiar, especially when we're talking about AI and cybersecurity, how fast that's moving, then you're definitely in the right place today.
Welcome to the deep dive. Our mission, really, is to cut through all that jargon. We want to give you a genuine shortcut to, well, being properly informed.
Yeah.
We're going to show you how AI, machine learning, deep learning, they aren't just abstract ideas anymore. They're incredibly important practical tools. They're out there actively solving real cybersecurity problems right now.
And we've got this fantastic handbook of use cases to really unpack.
Exactly. We'll guide you through the how and the why behind AI defending our digital world. Think of it as your essential guide, your shortcut to understanding what's happening on the front lines.
That's right. And if you're wondering, okay, why this deep dive now? Why is it so timely? Well, think about this. A lot of critical cybersecurity tasks, like reverse engineering, they still rely so heavily on manual human effort.
Oh, absolutely. Hours and hours.
Even with powerful tools, IDA Pro, GDB, PE viewers,
Yeah.
it's still painstaking work for analysts. AI really promises to cut that down dramatically, free up that invaluable human expertise for other things.
Precisely. And it's not just about saving time, though. That's huge. We've struggled for ages with accurately classifying threats. Is this file malware? Is this network traffic malicious? AI aims to give that accuracy a serious boost. And think beyond that about the limits of current cyber ops. Human brains just hit a bottleneck with these massive amounts of data. We often see fragmented views, sometimes even outdated thinking. Remember SolarWinds?
Yeah, or Colonial Pipeline.
Exactly.
Yeah.
Those incidents highlighted the problem. Plus, there's often a big gap between junior analysts and the real experts. This is where AI steps in. It offers agility, cost savings, better prediction, much-needed automation.
So even successful tools we already use, like fuzzing, they can get better with AI.
Definitely. They can be made much more efficient. AI can guide them better.
It really sounds like a fundamental shift then. Now, what's really unique about the source material we're looking at today, this handbook, it's not just another academic paper, right?
Not at all. It offers a hands-on kind of jumpstart experience. It's really designed for practical learning. You get actual code snippets, data sets. It details the entire machine learning pipeline for specific use cases.
The whole thing, soup to nuts.
Pretty much.
Yeah.
And that's the real value. It emphasizes this idea of a unified deep learning pipeline, a systematic way to apply DL in cybersecurity.
Okay.
Now, specific problems might have their quirks, sure, but this pipeline generally involves two workflows. Set A is about generating and training the models, data annotation, processing, training.
Building the brain, basically.
Yeah, kind of, yeah. And then set B is about consuming and deploying those trained models. But crucially, it highlights that designing the right data structure, that often needs deep cybersecurity domain knowledge. You can't just be a data scientist. You need to know security.
You need to know what data matters. You can't just throw everything at it.
Exactly. It's about knowing what to look for in the first place.
Okay, so let's unpack this. Let's get into some tangible examples. First up, AI for malware detection. This seems like a big one.
Huge. And it's a multifaceted approach. Let's start with something probably in your pocket right now. Android malware.
Right. Viruses, Trojans, ransomware.
Adware, spyware, phishing apps.
Yeah.
It's a constant stream trying to get onto your device. App markets like Google Play, they do a lot of screening, but things still slip through. They play a critical role, though.
Can you walk us through an example? Like, how does a nasty piece of Android ransomware actually work? How does it lock you out?
Sure. The handbook details one variant found back in October 2020. It was pretty clever. It exploited the system alert window permission.
What does that let an app do?
It lets an app draw a window on top of everything else, so it can completely hijack your screen, make the phone unusable.
Okay, nasty.
But this one went further. It used fake call notifications, and it manipulated something called the on-user leave hint function.
How did that work?
Well, it popped up a notification that looked like an incoming call, trying to get you to interact immediately, but then it tied that to showing the ransom screen. And that on-user leave hint function, which normally runs when an app goes into the background, the malware overrode it. So every time you tried to leave the ransom screen, boom, it just brought it right back to the front, relentlessly. Lock screen, ransom note, always in your face. It's a very sophisticated chain of actions.
That sounds terrifyingly effective.
Yeah.
So how does AI help deal with something like that? Interestingly, the handbook first mentions a solution called API Checker, which you said doesn't use deep learning.
That's right. API Checker is a deployed solution.
Hmm.
It uses dynamic analysis, basically, running apps in emulators. It uses exposed hooking to watch what the app does, extracting metadata like permissions APIs it calls intents it uses.
Okay.
But what's really fascinating is the feature engineering. There are over 50,000 Android SDK APIs,
A
right?
huge number.
But API Checker found only a tiny fraction, maybe 426, sometimes even just the top 150 were actually key for detection.
Wait, fewer APIs were better. That seems backwards. Why?
It's a brilliant optimization, actually. Fewer APIs meant much faster dynamic analysis. Critical if you're checking thousands of apps daily.
Right, scale matters.
And it improved accuracy, too, by focusing the tracking. Plus, these chosen APIs seem to complement each other well. They picked ones highly correlated with bad behavior, ones needing risky permissions or doing sensitive stuff.
And did it work?
Oh, yeah. Just adding simple auxiliary features like the permissions requested and intents used boosted precision way up from like 96.8% to 98.6%.
Recall.
Recall jumped too from 93.7% to 96.7%.
Wow. That's impressive for a non-DL approach. What's its real-world impact been like?
Very significant. Deployed since March 2018, it checks around 10,000 apps daily, average analysis time. Just under 2 minutes per app.
That's fast.
Super fast. And it was detecting about 2,400 suspicious apps per month with consistently high precision and recall, over 98% and 96% respectively. Of course, they had to keep updating it monthly for new apps and SDK changes.
Okay, so API checker is good, but it's not deep learning. Why do we need deep learning then? What are the blind spots, especially when we switch to, say, PC malware?
That's a great question. Rule-based systems like API Checker are good, but they struggle when attackers get tricky. PC malware is notorious for obfuscation.
Right, encrypting code, reordering things, adding junk code.
Exactly. Traditional signature-based detection just gets bypassed easily. This is where deep learning really shines. It can learn complex patterns that are hard for humans to define rules for, especially when the malware's appearance is constantly changing.
So how does DL look at PC malware differently?
It transforms the binary code into different data types that neural networks are good at analyzing. 3 main ways. First, images.
Images, how?
You take the raw bytes, convert them to pixel values 0 to 55, and reshape them into a grayscale image. Then you can use powerful computer vision models like ResNet 50. These are often pre-trained on millions of real images.
So the AI literally learns to see malware like a picture, like facial recognition, but for code.
Pretty much. It's a really innovative approach.
The second way is sequential data.
Treating it like text.
Sort of. The binary is seen as a long sequence of bytes broken into chunks. Then you use models like bidirectional RNNs, LSTMs, or GRUs are common, which are great at understanding sequences like language or music.
Okay, so it reads the code sequence. What's the third way?
Graph data. Malware code can be represented as a control flow graph, or CFG. Nodes are basic blocks of code. Edges show how control jumps between them. Tools like Angry can help extract these CFGs.
Then you use graph neural networks, GNNs. These are designed specifically to analyze interconnected data, like social networks, or in this case, the structure of the code's flow.
So image, sequence, or graph. Does one work better than others?
Actually, all 3 deep learning approaches show really good performance for PC malware. It shows how adaptable DL is. You can pick the representation that makes sense.
It sounds like AI is definitely getting an edge here, but is the fight over?
Oh, absolutely not. It's an ongoing battle. Attackers are constantly developing more sophisticated obfuscation, semantic NOPs, register reassignment, instruction substitution, code transposition. They're always trying to fool these AI systems, too. It's a constant arms race.
Okay, so detection is one thing, but AI's impact goes deeper, right? Into actually understanding the code. Let's talk reverse engineering. You mentioned it's super labor-intensive manually.
It is. Extremely. Imagine trying to figure out compiled code, maybe malware, maybe commercial software, with no source. Analysts have to guess where functions start and end, trace data flow, control flow, infer what it's doing. It's grueling.
So what specific RE tasks can AI automate?
2 key ones highlighted here. First, function boundary identification. Give the AI raw binary bytes, it tells you. This function starts here, ends here. Next function starts here.
Wow, okay. That alone saves a lot of guesswork.
Definitely. Second is function signature generation. The AI predicts crucial info about a function. What type of value does it return? How many parameters does it take? What are their types?
Like, it could figure out a function acts just like stroked by from the standard library.
Exactly. It could predict it takes 2 character pointers, returns 1, that kind of inference.
But compilers? They spit out such different binary patterns depending on settings, optimizations, and then obfuscation on top. How
Hmm.
does AI learn through all that noise?
That's the core challenge, and why traditional rule-based methods just fall flat. Deep learning excels because it's so good at learning complex data representations, especially if you have enough data.
How does it see the binary code to learn?
Different ways. Simplest is raw byte encoding. Just treat each byte as a number. Straightforward, but might hide the meaning. Better is encoding of disassembled instructions. Use the actual assembly parts, opcodes, operands. Those carry more semantic meaning.
Makes sense.
But the most advanced is representation learning. Here, the AI automatically learns its own vector representation for each instruction. This makes it much more resilient to obfuscation techniques.
So it's teaching itself the language of binary code.
In a way, yes. And the gold standard approach mentioned is using a pre-trained model, like Palm Tree. This is a huge deal.
Why pre-train?
It saves massive amounts of computation and data. The model has already learned general code structures from huge unlabeled data sets. It's like hiring someone who already speaks the language, rather than teaching them from scratch.
How do they pre-train it? What does it learn?
Palm Tree uses clever tasks. One is a masked language model, like fill in the blanks for code. It predicts hidden parts of instructions, learning their internal structure.
Okay.
Another is context window prediction. It learns what an instruction means by seeing what instructions usually appear nearby, like learning a word from its context in sentences. And diffuse prediction. This teaches it about data dependencies, how the output of one instruction is used as input for another. That's fundamental for understanding code flow. This deep learning gives it that shortcut for reversing even complex, obfuscated code.
So once you have these trained models, where do they get used? And are there still big challenges?
They can be plugged into existing RE platforms like IDEA Pro, maybe Ghidra, or offered as online services. But yeah, challenges remain. Getting models to generalize across different platforms, compilers, optimization levels, that's still tough.
Mm-hmm.
And extending AI to more complex tasks, like generating full control flow graphs, or data flow graphs automatically, or understanding memory layout and data structures. Those are still big research areas. Current stuff focuses mostly on the code instructions themselves.
Okay, staying with code. What about detecting similarity? You mentioned it's really hard to tell if two binaries came from the same source code if they were compiled differently.
Extremely hard. Different compilers, different optimization levels, like O00 is a 1 in the C example, different processor architectures.
Mm-hmm.
They can make the resulting binary look completely different, even if the underlying logic is identical.
Why is detecting this similarity important?
Think about finding known vulnerabilities in different programs, or tracking malware families that reuse code, or even detecting software plagiarism. It's crucial.
So how do they train AI for this? Manually labeling similar binaries sounds impossible.
It pretty much is. So researchers get clever. They take the same source code and compile it many times with different settings, different compilers, optimization levels, architectures. This automatically generates labeled pairs. These two binaries are similar from the same source. These two are dissimilar.
Uh-huh, okay. Smart way to create training data. And how does the AI see the code to compare it?
Two main ways again. First, sequence representation, like with PC malware. Treat the raw bytes as a vector, or maybe a 2D bitmap image. Simple, fast, but can lose deeper meaning.
Right. What's the other way?
Graph representation. This is where it gets more powerful for robust analysis. They use attributed control flow graphs, ACFGs.
Attributed. What does that mean?
It means the nodes in the graph, the basic blocks of code, have features or attributes attached. Things like how many string constants are in this block, how many function calls, how many arithmetic operations, plus graph structural features like how many outgoing edges does this block have.
And why is that better?
A key advantage is that this representation becomes largely architecture independent. The structure and the types of operations matter more than the specific machine instructions.
That makes sense. A big advantage. So you have these representations. How does the AI actually compare two pieces of code?
It uses a really elegant architecture called a Siamese network. You see this used a lot in things like face recognition.
How does it work?
It has two identical subnetworks. They share the exact same weights, the same internal knowledge. One network processes the first code sample. The identical twin processes the second code sample.
Okay, two identical brains looking at the two inputs. Then what?
Then they're trained using something called contrastive loss. It's designed to push the outputs, these high-dimensional embedding vectors, for similar code samples closer together. And it pushes the vectors for dissimilar samples further apart.
So it learns similar things look like this, different things look like that.
Exactly, but with the nuance.
Mhm.
It pushes dissimilar things apart only up to a certain margin. It doesn't waste effort pushing already very different things infinitely far apart. It learns the boundary, the threshold of similarity.
That's clever. How well do these Siamese networks perform? And any catches?
Both sequence-based, using CNNs, and graph-based, using GNNs models, actually show really high performance. The graph model needs a bit more domain knowledge up front to select good features, but it's often easier to customize or extend later. The sequence model is simpler, maybe faster, but less flexible.
And the catch?
A unique challenge is with active learning. Because a Siamese network outputs these embedding vectors, not a simple probability or confidence score, it's hard to tell which new, unlabeled samples the model is most confused about.
So you don't know which ones would be most valuable to label next.
Right. So you might actually need another AI model just to predict the main model's confusion or uncertainty. It's an interesting sort of meta problem.
Huh. AI helping AI learn better. Okay, let's shift gears. AI for detecting the unexpected and organizing threats. First, anomaly detection in sequential data, like network logs or system logs.
Exactly. Cybersecurity systems are constantly watching these streams of activity. Anomaly detection is all about spotting unanticipated changes, deviations from what's normal, hoping to predict or detect attacks.
And you're dealing with huge amounts of data here.
Massive. The handbook mentions datasets like UNSW MB15, that's a mix of real normal network traffic and synthetic attacks like fuzzers, worms, exploits, millions of flows. Or SOSP 2009, which is HDFS console logs, system events, again, millions of entries.
How do you even process that raw data into something AI can understand?
Good question. Raw log lines get converted into standardized log keys. But importantly, they're often enriched with add-on strings,
Add-on strings? Like what?
like differentiating between IP addresses on the same local subnet versus IPs connecting from the wider internet. Little details that provide crucial context for the AI.
Okay, got it. Now, this next bit sounds really insightful. Traditional anomaly detection often just looks backward, right?
Yeah.
Predicting the next event based on the past.
Often, yes, simple prediction. But this use case employs a bidirectional LSTM model, and this is a key difference.
Bidirectional, meaning
It doesn't just look backward in the sequence of events, it also looks forward. It analyzes the events flowing in both directions to get a complete picture of the context.
how does looking forward help find anomalies?
The handbook gives a great example. Imagine a sequence of operations where step C should logically follow step B, maybe resulting in an exception later. A forward-only model might see step B and think everything's fine because it can't see the future missing step C or the resulting exception. But the bidirectional model sees the whole sequence context. It sees step B, looks ahead, sees the exception, looks back, and realizes, wait, step C is missing here. This sequence is structurally abnormal. It identifies that missing causal link.
So it's not just about spotting weird individual events, but spotting when the whole story doesn't make sense. The structure is wrong.
Exactly. It can detect much more subtle, sophisticated attacks that disrupt the normal flow or structure of operations, not just single weird events. It understands the expected narrative.
That's a significant step up. How do you deploy these kinds of models? And are there still open questions?
Ideally, you deploy them for real-time classification. That often means containerization, using things like Docker and lightweight execution environments, maybe TensorFlow Lite, to keep things efficient.
And the challenges.
Big ones include, how do you handle genuinely new, never-before-seen event keys without crying wolf all the time? False positives. And can the prediction criteria be smarter than just simple thresholds based on probability ranks? Still active research areas.
Okay, final application area. Scalable malware clustering. This sounds like dealing with sheer volume.
It is. Anti-malware vendors get thousands of new samples every single day. Manually analyzing each one. Impossible.
So they need a way to group them, prioritize.
Exactly. Find the novel threats quickly, group the similar stuff together so one analysis covers many samples. The solution here is behavior-based clustering using unsupervised machine learning.
Behavior-based. So focusing on what the malware does, not just what its code looks like.
Precisely. The pipeline starts with dynamic analysis. Run the malware in a sandbox. But crucially, it involves taint tracking.
Taint tracking, what's that?
Imagine putting a little radioactive tracer on sensitive data, like a password typed in, or a specific file path. Taint tracking follows that data as it moves through the malware's execution.
Okay.
Tools like Panda help with this. You see which system calls use the tainted data. You see control flow decisions like if statements that depend on tainted data. You see network activity involving tainted data. It builds a detailed behavior profile.
So you get a rich picture of its actions. Then what?
Those profiles get turned into structured feature sets. Things like performed operation X on file Y or compared tainted value A with tainted value B. Then comes the scalable part, locality-sensitive hashing, or LSH.
LSH sounds complex. How does it help with scale?
It's actually quite magical for this. The core idea of LSH is that similar input items are likely to hash to the same bucket. Dissimilar items likely go to different buckets
So it groups similar things together quickly.
very quickly and without comparing every single sample to every other sample, which would take forever. It uses Jacquard similarity to measure how alike two malware samples, represented by their feature sets, are. Basically, shared features divided by total unique features.
Okay. How does LSH technically achieve that?
It uses a couple of tricks. First, min-hashing. This condenses the potentially large sparse feature sets into much smaller signature matrices while cleverly preserving the Jacquard similarity between samples.
Pull smaller fingerprints that still capture similarity.
Right. Then LSH takes these signatures and divides them into chunks called bands. It hashes each band separately. If two malware samples happen to hash to the same bucket in any of these bands, they're flagged as a candidate pair for being similar.
Why the bands?
It creates this useful S-curve probability effect. If two samples are above a certain similarity threshold, they're very likely to match in at least one band. If they're below it, they're very unlikely to match in any band. It efficiently filters out the definite non-matches.
Like a bouncer letting in only the couples that look similar enough?
Yeah, something like that.
Yeah.
It focuses the effort on the pairs that are likely to be truly similar.
So LSH finds the candidate pairs. What's the final step?
Those candidate pairs are then usually refined and fed into a standard hierarchical clustering algorithm. The handbook mentions single linkage agglomerative clustering, using Jacquard distance to actually form the final groups or clusters.
What's the impact for the anti-malware companies?
It's huge. It lets them manage that overwhelming flood of new threats. They can automatically find behavioral patterns, group similar threats, and let their human analysts focus their precious time on the truly novel or most dangerous stuff. It brings order to the chaos.
It's a real force multiplier. Are there limitations, though?
Sure, even with LSH, truly massive datasets can still push computational limits. And malware can be tricky. If it's specifically designed to act very differently in the sandbox, even if its core goal is the same, that could potentially fool or weaken the behavior-based clustering. It's still a cat-and-mouse game.
Wow, we've covered a lot. We've taken this really fascinating journey today, haven't we? Diving deep into how AI isn't just theory in cybersecurity anymore. It's a practical, multifaceted tool, really changing the game.
Absolutely. From automating that painstaking reverse engineering, detecting those subtle anomalies in logs, recognizing malware from its picture.
Or grouping it by how it behaves.
Yeah. AI is providing these incredible shortcuts to understanding complex threats. It's empowering defenders in ways that honestly were unimaginable not that long ago.
So for you listening, you've now got this cutting-edge understanding, really, of how AI is being used right now in the trenches of cyber defense.
And think about how these approaches, seeing patterns in code, watching system behavior, even inferring cause and effect, they kind of mirror how human experts think, don't they?
Yeah, but at a scale and speed that humans just can't match. Tirelessly.
Exactly, that relentless scale.
But that scale brings up a final thought. As AI gets better and better at defense, doesn't it also create new possibilities for attackers using AI?
That's a million-dollar question, isn't it?
Yeah. So here's something for you to mull over. This constant evolution of AI in cybersecurity, is it just leading to an ever-escalating arms race? Or could it, maybe fundamentally, shift the advantage towards the defenders? Could we eventually build a kind of truly robust digital immune system for our world?
A provocative thought to end on. That's all for this deep dive.